Okay, thanks Google. For those of you at home, this is the 15th time I pressed the Go Live button. Well, perhaps I'm slightly exaggerating. It was not 15, it was only about 10 plus. Okay, so we are back live, and as promised at the end of the previous course session, we are going to now move into the world of vector geometry. So this will complete our short excursion in linear algebra. We are going to look at vectors with geometrical eyes. We're going to then move on to giving a way of writing equations for lines and planes. You will see that this is conceptually not mind-boggling stuff, and I hope you will agree with me after we examine these concepts in some detail. Now, first of all, we have already seen vectors, mostly from an algebraic perspective. For us, so far, a vector has been nothing but a tuple of real numbers. So, for instance, tuples of length 2 of real numbers correspond to sets of points in the Euclidean plane, and we've been writing them as vectors, xy vectors like this. We also have been looking at vectors in R3 or other dimensions, but R2 is where I stopped drawing, for good or for worse. Now, in physics, vectors play a fundamental role, and they usually are used to measure quantities, for instance, velocity. Now, in physics, a vector is something which has a direction and a magnitude. And the magnitude measures somehow the strength of the vector. It's usually the length of the vector. So, for instance, the direction tells you of a velocity vector tells you in which way you're actually driving, for instance, your car, and the length of the vector is a measure of how fast you're driving. Then perhaps you may even have a vector that tells you how drunk you were when you were driving, but I hope that doesn't happen to you. Now, you may ask, what is the connection between these two viewpoints? Why is it that so far in the course, we've been happy to abstract a physical quantity normally represented by a vector as a tuple of points? Because somehow when you think of a vector in space, you think of the vector as having a start point, an end point, and a direction and the length, which is determined by the start and the end point, typically. Why can we just abstract all this information away and represent it as computer scientists as just a tuple of points, a one-dimensional array? Well, let's see. In fact, what we do is somehow more abstract, or at least as abstract. It allows us to capture even the vectors as the physicists like to view them. So let's look at some examples. Let's draw. As I said before, I'm only going to draw examples in 2 dimensions, and for 3 dimensions, well, you're on your own. Okay, so a vector, for instance, could be something like this. Oh, so this is a point. It's a vector that starts from a point P0, whose coordinates are 1, 0, and goes to the point P1, which would be this one, whose coordinates are 2, 1. Sometimes you will see a notation like this. That's a vector that sort of tells you somehow in what direction it is going. It's going to go up 45 degrees, and whose length I think we can typically calculate in this case using Pythagoras' theorem. So what would be the length of this vector?
Well, you have to like, it's 1 by the power of 2 and
Square, yeah, it's square root of 2, as people are saying, because square root of 2 is exactly the length of the diagonal of, so this, the two sides of the rectangle are length 1, so it's square root of 2. So whenever you have a vector, typically the length of the vector is denoted like this. So that's the length of the vector v. In this case, the length of this vector is going to be square root of 2. It's a non-negative number. Okay, now suppose that I look at this other vector here. Well, not exactly this thing. It starts in the origin. Jesus. Goes up 45 degrees. It starts at 0, 0, and it goes to 1, 1. So that's a vector that goes from the origin, let's call it O, to this other point, which let's call it P. So it's the vector OP. It goes from 1, 0 to 1, 1. Again, up 45 degrees. Question. Is the vector OP different from the vector P0, P1? When are two vectors equal? Well, two vectors are equal.
when they have the same distance, same direction.
Absolutely. Two vectors are equal, as your colleague is saying, when they have the same direction and they have the same length. Now, the vectors OP and P0, P1 are both going up 45 degrees. So they have the same direction. What is the length of OP? Well, again, it's square root of 2. So these are two equal vectors, even if we actually write them in two different places in the plane. Because two vectors are equal independently of where they are placed if they have the same direction and the same length. So they're actually the same vector, even though they are placed differently. In fact, if I just were to translate the y-axis by one step to my, well, to your right, then, well, P0, P1 would be exactly OP, wouldn't it? So basically, what we do when we represent a vector like this as the point 1, 1 is just to say we assume that all vectors are actually rooted in the origin of my coordinate system. Since one of the endpoints of the vector, which is called the tail of the vector, is always going to be the origin, the only thing I need to remember is the endpoint of the vector, namely the tip. And the fact is that all vectors can be represented in that way. That's why it's okay to look at them simply as tuples of numbers. So I've introduced this terminology of the tip and tail. So this point here is the tail of the vector. This point here where it terminates is the tip of the vector. So basically, these two views are the same. Okay? So there is no conflict between the two of them. It is perfectly okay to consider vectors as always rooted in the origin. That's why the good data structure of a one-dimensional array of the appropriate size is enough to represent a vector like the physicists like to do. Now, of course, I could give you a more very precise definition of an equivalence relation over geometric vectors that tells you that each equivalence relation has a representative in the equivalence class, which is a vector rooted in the origin. But unless you ask for it, I'm not going to do this. Why? Because some people get scared. Equivalence relation, what's that? In fact, let me ask you, what is an equivalence relation? Because, I mean, discrete math 1, I'm sure you saw equivalence relations. When is a relation an equivalence relation? Yeah, when it is reflexive, transitive, and symmetric. It's basically the properties that the notion of equality has, but equivalence is more general than just equality. I'm equivalent to myself. That's reflexivity. If I am equivalent to Sigurdur, Sigurdur is equivalent to me. If I'm as tall as Johnny, and Johnny is as tall as Frank, then I am as tall as Frank. That's transitivity. These are the three properties. They are not mind-boggling, but the important thing is that basically an equivalence relation allows us to abstract away from unnecessary details here. And in each equivalence relation of vectors, of geometric vectors, there is one which is a representative for that equivalence class, which is a vector rooted in the origin that goes up by the right angle and that is as long as it needs to be. So for instance, if one considers a vector anywhere here, which is of length from some point A to some point B, where the length of the vector AB is actually square root of 2, and this vector goes up 45 degrees, then this vector is nothing but the same as OP and the same as P0, P1. It's just placed somewhere else, somewhere. And what does it take for this vector to be in the same equivalence class as OP and P0, P1? Well, the only thing that it takes is that A has the form XY and B has the form X plus 1, Y plus 1. All of the vectors of this form actually are the same as the vector that goes from the origin to 1, 1. Okay, so we've introduced some terminology. We've seen that actually we can place vectors anywhere, but we can in particular place them at the origin. So let's see what next. I've already given you this terminology on the fly, so that's good enough. I've already given you some examples, and I've already shown you when two vectors are equal. And we've already examined what the relationship with vector is, all on the previous picture. So let's look at some formula now. There are several things on these slides which are labeled as theorems, which means that they can actually be proved. I'm most of the time just giving you examples without proving anything. Because in fact, there's really nothing to prove. It's something that you've seen all the time. So for instance, two vectors are equal if and only if they have the same coordinates. Well, yeah, two arrays are equal if they contain the same information, point by point, entry by entry. For computer scientists, that's the damn thing. How do you calculate the length of a vector? And now this vector, we can always assume is rooted at the origin. So the only thing that matters is its coordinates x, y, z. Well, you just basically use Pythagoras' theorem. In this case, in 3 dimensions. Why? Well, suppose, and let me work in 2 dimensions. Suppose here I have my vector, my coordinate system. and I have my vector here, and I tell you, okay, this is x, this is y. What is the length of this vector? It's the length of this line segment here, which happens to be the diagonal of a square triangle. And since you were at elementary school, you can calculate the length of this diagonal. It's nothing but the square root of x squared plus y squared. That's Pythagoras' theorem. If you do it in 3 dimensions, it's exactly the same. You just need to add a plus z squared. You know, you thought you had forgotten or you had got rid of Pythagoras once and for all? Well, you haven't, really. Actually, Pythagoras was a very interesting guy. Extremely interesting. You know, his people were also the guys who showed the square root of 2 is not a rational number. So you cannot write it as a fraction. And the discovery shattered so much the philosophy that Pythagoras was so, well, first of all, they found this was an amazing discovery. So they slaughtered several hundred lambs to celebrate. But then Pythagoras thought, okay, my whole philosophy is based on the fact that there are only rational numbers. And now somebody from my group actually showed that this thing, square root of 2, is not a rational number. So what do I do? So he prevented everyone. So he did like the NSA that became a national sectarian secret. And apparently probably also killed the guy who showed that. But that's another matter. Anyway, end of story. Some people complain that I tell too many stories. Well, there you are. Sorry. That's the way I am. Storytelling is how we teach people. We've been teaching people since the beginning of time. So it's also a way of not to make this stuff particularly boring, as it could be. So back to us. Pythagoras tells us how to calculate the length of vectors. What else? 2 things about length. There is only one vector which has got 0 length. And guess what? It's the 0 vector. Well, you can tell it from the formula. If either x, y, or z are not 0, then this thing is not going to be 0. And the 0 vector, as your colleague is saying, is basically a point. It is a point. Absolutely. It has length 0. It started a point. It can't move. It stays there. So it stays in the origin. It's a cozy place to be. It's like in the womb. You never want to get out, but you have to at some point. The second thing, or the fourth thing that I would like you to focus on is how computing the length of a vector interacts with scalar multiplication. So if you have a vector v, you can scale it up or down by multiplying that vector by some number. So for instance, if you want to shrink the kid, you multiply it by some a which is smaller than 1. Hopefully not 0, otherwise you shrink the kid to a point. And then you cannot get out. It's like a black hole. But if you multiply the 0 vector by anything, you get the 0 vector back. So don't shrink it too much, unless you want a point. Okay, so what is the length of a times a vector v? Well, that's easy. You compute the length of v, and you multiply it by the absolute value of a. Now, what is the absolute value? Well, if I give you -3, the absolute value is 3. You just forget about the minus. Why do we have the absolute value? Well, because nothing has negative length. Oh, the question is, are you not allowed to scale in the other direction? Yes, you are. You're allowed to do that, but the length of the vector is always going to be positive. So that's the point. So we're talking about the length. So in particular, So that this means that the length of a vector does not depend on the direction of the vector. Example. So if I take this vector as I did before, going from the origin to here, the vector is directed this way. So this is O, this is A. So that's the vector from O, I go to A. But you can also take the vector from A, I go to O. This would be the black, well, not quite black. This vector here. Well, what is the length of these two vectors? Well, it's just the distance you travel from O to A. It's the same distance from A to O. That's why the length is the same. And basically, by multiplying a vector by -1, you just change the direction of the vector. That's what you do. Instead of going from O to A, you go from A to O, which corresponds to the vector that from the origin goes to the point -1, -1, instead of going to 1, 1. It's the same vector, because it goes in the direction downwards 45 degrees of length square root of 2. So far, so good? It's mostly pictures, actually. So for you who are pictorial guys from the YouTube era, this is fine. For me, I'm sort of an algebraic guy from prehistory. I prefer to write X, Y, Z myself. But here I thought I'm doing myself a disservice and I will draw. Okay, yeah, well, there you are. Sort of, we answer questions before they're even asked. So what is the geometric view of the negative of a vector? Well, we just change direction. But hey, in fact, we can connect this thing with something that we were doing just before. Let me draw this again. Or perhaps I should say, let me try to draw this again. So here's we have our point 1, 1, and that's the vector. Sort of, that's the origin. That's my point 1, 1. Okay, so if I take the negative of this vector, what is it that I get? Exactly the thing that we were saying before. I get the point -1, 1, -1. So let's do it in blue here. But how much do I need to rotate the point 1, 1 to bring it to -1, -1? You need to rotate it by 180 degrees. So if I apply the transformation R180, and really now it doesn't matter whether you do it clockwise or anti-clockwise because it's the same. So you just transform this vector 1, 1 into -1, -1. You just rotate it like this. And what's the matrix that does this? So you have -1 here, -1 here, 0, 0. Why? Because what is the cosinus of 180? Well, it takes the point 1 to -1. So that's why we have -1, 0. And what does it do to the point 0, 1? It takes it to the point 0, -1. So that's the matrix. And if we multiply this matrix by our point 1, 1, what is it that we get? -1, -1. In fact, if we multiply using this matrix, a vector xy, we are going to get -x, -y. So basically, when you have a vector and you put the minus in front of it, you're multiplying implicitly by, you're doing a rotation by 180 degrees of that vector, which could be obtained, in this case, in a more complicated way by doing a matrix multiplication. In this case, it's actually easier to write a minus in front of the vector because it does exactly the same thing. Okay, so whenever we are putting a minus in front of a vector, you're doing 180 degrees rotation. Or in other words, you're taking that vector by changing the direction. Instead of going from the tail to the tip, you go from the tip to the tail. Yes? The question is, does it matter which way you rotate? In this case, it doesn't matter because you go 180. You will go to the same place no matter whether you rotate clockwise or anti-clockwise. Absolutely. Good question. Okay, so this sounds like natural. But, you know, I mean, I never thought myself that minus was just rotating by 180 degrees. Well, sort of. It certainly is true, actually, for the number system. But numbers are just on a line. Eh? So if you take 35, you take minus 35, you travel in the opposite direction. But negating a vector is just one of the operations. How about addition? So what is it that you do when you add two vectors? Well, you sum the components of the vectors one by one. What does this mean geometrically? Let's see. So if you're an algebraic guy like me and you take two vectors, x1, y1, x2, y2, and you sum them together, well, the result is going to be a vector which is x1 plus x2, y1 plus y2. Let's see algebraic view. Of vector addition. And in fact, that's the computer science view of vector addition because that's what you do. I give you two arrays of numbers. I want you to give me an array that contains the sum of the numbers pointwise. You do a for loop and you do this. That goes through the two arrays and sums the results and put them in the return array. Easy peasy. That's actually what it does. But pictorially, what is it that one is doing when one is doing this? So let's look at an example. And God help me with the drawing. Okay, suppose that I have this vector here, which is the vector that corresponds to the algebraic vector 2, 1. And let's say that I have this vector here. Warning, drawings are not to scale, which corresponds to the algebraic vectors vector minus 1, 1. Suppose I sum them together. The formula that I have above tells me that the result is going to be 2 plus minus 1, that's 1, and then I have a 2 here. So it's going to be this vector here. Now, what is this vector? Well, these two vectors that we started from they actually are the two sides. They determine something which is called a parallelogram. And like this. Okay, so this is it's a parallelogram. You just take two parallel sides on both sides. And you know what? The sum of the two vectors is actually the diagonal of this parallelogram. Spanned by the vectors. These two vectors here.
I don't think I can read that already.
Oh, you can't? Which writing can't you read?
You just wrote there, isn't it?
Yeah. The whole of it. Okay, I think I said it in words too. It says diagonal of the parallelogram spanned by the vectors. I don't think I would do block capitals right now. There is another way of looking at this. I'm doing the sum of the vectors of the vector 1, 1, 2, 1, and minus 1, 1. Now look at what happens. Okay, so 2, 1 is this red vector here. Now I'm making it red right now. Suppose that I actually take the tail of this vector and I connect it to the tip of the vector minus 1, 1. In other words, I move it here. If I follow the two vectors one after the other, look where I end up. I end up at the vector which is the sum of the two. This is something that people call the tip-to-tail rule. Summing two vectors means you actually move one of the vectors and you connect it to the tip of the other one. And the point where you go to is exactly the sum of the two vectors, which kind of makes sense. Why? Well, remember, a vector is something that you can follow in space, in the two-dimensional space. I start from the tip of that vector, so from the tail of that vector, and I follow the vector and I end up at the tip. Then I follow the other vector by the amount and the direction of that vector. And where do I go? I have traveled in the direction of the sum by the amount, which is the sum of the two vectors, which is the length in space that I've traveled. And that's what I have traveled. Now, following the two sum vectors is typically not the shortest path, but if you go along the diagonal of the parallelogram, that's the shortest path, and that's actually the sum of the two vectors. Yes? Okay, so the question is, or perhaps it's not a question, it's a statement. The same goes for multiplying a vector, I guess, by a scalar. Oh, summing many vectors, you're saying. Okay, so I misunderstood the question, yes. So, well, you can sum more than two vectors, and that's exactly the same. The same applies. Because you can sum them two at a time. So you can sum the first two, and you do it by following this. Then you sum another one. And this means you move you follow the tip-to-tail rule, you move the tail of the new vector to the tip of the sum vector that you got before. And you keep doing that. Absolutely. Okay, the question is, what about the minus? Good question. And that was going to be my next point anyway. So let's see. So suppose that this is my vector u, and this is my vector v. And this is the vector u plus v. Okay, so what is u plus v minus u? It's this thing. It's this thing. Why is that? Well, because we have actually taken away this part by removing u. So it fits nicely with what you had before. So this vector here, the diagonal, is actually the sum of these two guys. If I remove u, well, then what I'm left with is only part of the journey, namely the v part, which is this bit here. Okay, so let's repeat it. Let's do a similar but not necessarily identical picture. So this is the sum of two vectors. And let's say it's by the tip to tail rule is this one. So we are summing these two vectors here. This is v, this is u, and this is u plus v. Okay, the question is, what is u plus v, that's a vector, minus u? Well, it's the vector that summed to u gives you u plus v. And what is it? Well, it's this one. This is the result of doing a subtraction of vectors. Why? Because, I mean, think about the journey. Okay, I want to go from here to here. And, well, the fact that I'm actually summing u and v means for work reasons, I'm supposed to go there first. And then from there, I go here. Okay, so how long is the initial part of the journey and in which direction does it go? Well, it's these two pieces of information are represented by the vector v. Which is the difference of the two. Okay, so what if you multiply? That's a question that I just got. Now, you have to consider two different types of multiplication here. One of them is the one that we were talking about before, namely scalar multiplication. You have a number and you have a vector. And you can multiply A by B. There is a different type of multiplication, which is called the dot product. And this is something that we will see later on. In fact, you've already seen it because it's nothing but matrix multiplication, but of vectors. In that case, you have two vectors, u and v, in Rn, so they must be vectors of the same length, and you actually do something which is called the dot product. This is nothing but you multiply them as matrices, so the result is a number. These are both fundamental operations. Let's look at the scaling. What does multiplying by some A means? Well, we've already seen an example. The example was multiply by -1. Because in that case, you take a vector v and you turn it into -v.
It either just increases the distance
Absolutely, absolutely. So you increase, absolutely. Your colleague is saying by multiplying, I'm doing a scaling operation. So I make the vector longer or shorter, depending on whether A is greater than 1 or smaller than 1. If A is smaller than 1, I'm not only scaling the vector, sorry, let me rephrase. If A is positive, then I scale up my vector V. If A is negative, I sort of, scale up is not the right, it's not the right word here. I scale V, but I don't change the direction. If instead I have A, which is negative, I scale V and change its direction. Now, the scaling could be scaling up or scaling down, depending on whether the absolute value of A is positive or whether it's between 0 and 1. And if A is 0, of course, you turn the vector into a point. So positive multiplication preserves the direction of the vector. Negative multiplication by a negative number changes the direction. Like we saw before, if you have a vector and you multiply it by -1, this means taking the negative of that vector, then what you're doing is to rotate it by 180 degrees. If your question is, if you're multiplying with another vector, then you're doing the dot product, and that will be the topic of the next lecture, amongst others. In fact, with the dot product, you can do a hell of a lot of things. Question? The question is, will the dot product of two vectors result in a single number? Yes, absolutely. This is exactly what you're doing when you're multiplying a matrix. You want to find out what entry is at position ij of that matrix. You're doing the dot product of the ith row and the jth column of the other matrix. And it results in a number. In fact, the dot product is exactly the operation that you do there. Okay, so happy drawing. Well, I should say happy data structures exam tomorrow, and may you survive. I don't know.